Okay, so let's get started. Any question from this time? This time we go over basically the properties of Laplace transform. Once again, they are similar to those of Fourier transform, but now we are but now everything we talk about, we need to think about the ROC. So lots of them has like ROC being the interval of the two ROC, but but you might also cancel some poles when you do the transform. So the ROC is most of the time being this union of two ROC, but it can get larger because you might cancel some poles. And so that's that. And then we start from this delta function and state function having Laplace transform being 1 and 1 over s, and also the negative state function on negative side is also Laplace transform goes to 1 over s, with 1 over the ROC being the right side, ROC being the left side. And we use the I think the differential formula. Yeah, we can use the differentiation formula to get a whole bunch of Laplace transform pairs also. So basically have this s to the n power, and also you can have this, and you will get some polynomial on the time domain. And also if the pole is not at 0, it's at s plus a, you can also do the similar thing to differentiation n's power, then get s on t to the n's power here. So that's that. And obviously the delta function can do a time shift, then Laplace transform, you get this e to the minus st, s times whatever amount your shift is, big T. And there's sine and the cosine. Excuse me. And yeah, sine and cosine, I believe you can just decompose sine. Once again, use the Euler equation. So you decompose cosine into the sum of two exponential, and you get this. And also sine into the difference of the two exponential, and I think you can also get this. And yeah, sine and cosine decompose into exponentials. And then you can also do Laplace transform of very singular things. You can do then on those unit doublet or n-slit, those u sub n, which is n's power, n's differential of the delta function. And want to do this because that's the Laplace transform of s to the n. Okay? And n can also be negative, then you will get back this. And this actually fits with the formula we talked before, right? So it's this one. This one is u minus n, as we calculated before in chapter 4. Anyway. Oh no, actually chapter 2. Anyway, so we want to do this because we also want to do the inverse Laplace transform of this s to the n, because we are basically dealing with rational functions. So we are going to break things into all these vectors. Okay. Any question about the Laplace transform of those rational vectors? If not, then okay, then let's go to the maybe the interesting part of Laplace transform. So very good application is Laplace transform give you a nice way to study the stability and causality of the systems. There is a very intuitive image to see it. And yeah, so we are going to use the Laplace transform of the system. So the Laplace transform of the impulse response is going to be now the system function big H of s. And just like in the Fourier transform, we also have this kind of equation. It's actually a little more general than the Fourier transform. But anyway, so you think about LTI system, and output Y is the impulse response, and convoluted with the input signal. Then once again, you can use the convolution property of Laplace transform. You see here, right? So you have x1 being small h and x2 being x, and then y of t equal to this thing. So big Y of s will equal to big H of s times big X of s. Okay. So this is also true. You basically just change omega to s. And then okay, now these two property. So stability and causality. So two things. So first one is you can read the Laplace. You can so so you have your TI system, and most of the time you can get the Laplace transform h of s. Sorry, the system function h of s, which is the Laplace transform of your impulse response, small h of t. Remember, we have lots of tests on what is h of t. It's a response when you put an impulse to your system. But anyway, that's not that important here right now. So the thing we want to say is, so you can see the stability of your test system by looking at the ROC of this system function h of s. And the system is stable if only if that ROC includes your j omega axis. So remember, your ROC is going to be one strip. So it might extend to the right, it might extend to the left. But anyway, if that strip contains your j omega axis, so contains s, which is RES equals 0, then the system is stable. And it's infinite leaf. Do we have a picture? No. Okay. I guess you can probably picture this. And we have a semi-derivation here. So we have this is a kind of reasoning for this being true, but the reference is not really complete. But let's go over it. So this means that so remember ROC. Well, we have talked a lot about how to determine whether a system is stable, right? So at the beginning, stability is defined as bounded input, bounded output. And in chapter 2, we say we start to study everything with this impulse response h of t. Okay. Let me state u as yeah. So at chapter 1, we have stability as bounded input, bounded output. Then chapter 2, that we get derivation that, and also lots of tests in midterm 1, right? Midterm 1, we test a lot about this. That is, we can characterize stability of a system by looking at this impulse response h of t. And is stable if only if h of t is absolutely integrable. And then now this thing is a little weird. Now in in chapter 4, we have the directional condition, which says that so the first one of them is the impulse response. Excuse me. How should I say? Okay. So in chapter 4, we have the Fourier transform of a impulse response converge. So the direction is if the h of t satisfy the directional conditions, then the Fourier transform will converge. Okay, and this h of t being absolutely integrable is one of the directional condition, the first directional condition. So you can see that there are lots of holes in this argument here. So first of all, this is only one direction. It says that h of t absolutely integrable, then you can get the Fourier transform converge. But the reverse, we are not sure is true. It converge, then h of t might not really be absolutely integrable. And also let's hold that it is the directional condition. There are three of them, but h of t being absolutely integrable is only one of them. So yeah. So from binding input bound to bounding input bounding output to h of t being absolutely integrable, that's infinite leaf. That translating to Fourier transform being converged is kind of questionable. But anyway, so that's some weird representation we have this in a book. But for now, we assume our function are kind of nice. So we assume that this is also infinite leaf. And yeah. So we think the system is stable if only if the Fourier transform is converged. And now we can back to this ROC business. So Fourier transform once again is the Laplace transform restrict to the real part of x excuse me, restrict to the j omega axis. And yeah, so the Fourier transform converge means ROC include the j omega axis. Okay. Yeah. So that's this is what we are just going to assume is being true throughout the later part of the course. So any question? Yeah, it is very nice. Maybe I can. Okay. Maybe I can sketch here. It would be nice. So yeah. So we have this S-plane, and it's kind of like if ROC include your j omega axis here, then you are stable. Then it's outside, then it's not stable. Then maybe you have pose here, something like that. Yeah. So ROC is stable if only if the, once again, if only if the system is stable if only if the ROC include the j omega axis, and which means the Fourier transform exists. And now you can kind of already see that why Laplace transform is more general than Fourier transform, because Fourier transform is useful only when it converge, and it converge only when the system is stable. So Laplace transform can analyze even a non-stable system. Okay. Whereas if you want to write the Fourier transform of your impulse response, then you can only do that if your system is stable. Okay. Any question? How to read stability from ROC? This is something you also need to remember throughout the course, and maybe over even after you taking a class. Okay, so that's stability, and the other C is causality, and and now we don't have if only if. This is quite untypical in this course. So we have necessary but not sufficient condition for the system being causal. Okay, and yeah, so we say if we want the system to be causal, then the ROC must be right-sided, and this derivation now is very clear. So also in chapter 2, we characterize the causality with h of t, and we say the system is causal if only if ht is 0 for t less than 0. Okay, so yeah, so in h of t need to be cut off t equals 0, so all the negative part need to be 0. And then h of t is a right-sided function. And when we do the Laplace transform of right-sided function, and the RC must be the right half plane, must also be kind of right-sided. Remember, it's one of the 8 property of RC we talked about. You have a left-sided function, then the RC needs to extend to the left, and you have a right-sided function, the RC must extend to the right. Okay, so let's draw a picture here, then maybe here. Yeah, so it's like you have some poles, and if you want it to be causal, then RC must be this one. Okay, the extend to the right. And so this is a necessary condition, but this is not sufficient, as we will see later in an example. The converse is not true, so even if you have a right-sided RLC, sometimes your system is still not causal. But if you get more condition, then so we say if the system is a rational system, which means that the big H of S is a rational function. We just say a rational system function. Then this RLC being right-sided is if only if to the system being causal. Okay. So this is only true if it's a rational system. It has a rational system function. Any question? If not, yeah, then let's see an example. Yeah, I think this is okay. Anyway, so we go back to the example of our favorite function. So this is exponential decay cut off at t equals 0. And now I think this is a system. This is an impulse response. So h of t is this exponential decay, and yeah, and this is causal, and also stable. Right. So you can read from h of t, and it's causal because you have u of t here. So for every t less than 0, h of t is 0. So maybe let me also sketch this function we see lots of time here quickly. Okay, look at this decay, and it's 0 on this side. Oh, sorry, what's going on? Yeah. So we can read from h of t. This is causal because this side is 0. And it's also stable because you integrate this, and its exponential decay is going to converge. Yeah, yeah, it's causal and stable. And then we can try this on Laplace transform. Laplace transform, we know this is 1 over s plus 1, and we pick the RC being bigger than -1, so it's like this. It has a point -1, and the RC is the right side. Okay, yeah, and RC is this side, and yeah. And we can see, so we check both conditions here, right? So it's stable because it contains the j omega x is here. And it's causal. Well, it can be causal because it contains the RC is to the right side. But it's actually causal because you have a rational function here. Okay. So that's that. Let you look at this a little more. So you have a impulse response being this is causal, is stable, and now we do a Laplace transform. Then you can kind of just read from the RC that this is causal and stable. So it's causal because it's right-sided and the system function is rational, and it's stable because it contains the j omega axis. Okay, and then let's get a non-directional one to see what we need to the directional condition. So now our system function is this. So it's similar to this s plus 1, but we have e to the s on the upper side. And so the pole plot is pole 0 plot is basically going to look the same. You also have a root as s equal to -1, and we pick out c to the right side. And so it's going to be stable, but it's not causal because we have constructed this as the Laplace transform of this function. So remember here we have this exponential decay and Laplace transform, the 1 raised plus 1. Then if we shift this exponential decay to a negative 1, okay? So we get plus 1 on t, so basically shift time in negative 1 direction. Then we can get the corresponding Laplace transform just using the time shift property. And if you look at the table, it is you get so this basically has t0 equal to -1, and you look at the formula, I give you e to the s here. So the extra e to the s means you do a time shift to -1. And yeah, and the RC doesn't change. It's same as what we have in the table. Okay. So anyway, so this thing has impulse response being this exponential decay plus shift to starting from t -1. But now this thing is non-zero between -1 is 0, and then yeah, this is not causal because if you want the system to be causal, then actual t needs to be 0 for every negative t. Okay, so yeah, so this is an example where your ROC is right-sided, so ROC is still this thing, right-sided, but the system is not causal, and that's because your system is, yeah, and that's because your system function is not a rational function. Okay, but it's still stable. If you do integrate here, it's still 0. Question? No? Okay. Yeah, this is quite an interesting example. Okay. Then, yeah, then we can now start to characterize this, do kind of detective work by by having a system function and decide its ROC by specifying whether the system is causal or not causal and stable or not stable. So for example, we have a system function here. So x -1 over x plus 1, x -2, and you can write the pole 0 plot here. So you have a 0 at 1, and a pole at -1 and +2. So here, a -1 plus 2, and you see there are 3 possible ROC, right? Because you have a 2 pole here, so ROC are bounded by pole is rational function. So it's either to the right, in the middle, or to the left. Okay, and we didn't say the ROC about this, but you can decide which one is the ROC by saying whether the system is causal or not, or stable or not. Okay, and yeah, and so as we said, if the system is causal, then it's necessary that the ROC is to the right side here. So it's ROC. If it's causal, this can be this is the only possibility. And yeah. So if it's causal, then you should pick this ROC, and we will show how to do the inverse. you do the partial fraction expansion, which we omit here, and you look up this one. Yeah. Then you decide each fraction where you want to use this formula or this formula. In this case, it's a right-sided formula for both. And yeah, then you get your inverse Laplace transform, which means the system function. Which means the impulse response here. And yeah, you can see this is causal because you have VLT here. And yeah, and here you see that you can see that this is not stable because it doesn't contain the omega axis, and thus it is actually not stable, and it's yes, because you have this exponential growth here. It's a +2, right? It is exponent e to a 2t, and it's going to grow with time exponentially. It's very unstable. And then your middle part, we have that if we want our system to be stable, then you need to pick the middle part, because this is the only possibility where your ROC will include this J omega axis, right? Obviously, is only this one include J omega axis. And yeah, so if you want a stable system, you will pick the middle ROC, and then you do an inverse transform, then you solve to this. So one with u of t, another with u of negative t. And you can kind of see it's exponential decay to a plus side and exponential decay to a negative side. So this thing is stable integrated. It's a finite value. And yeah, but it's not causal because you have this negative time component. And finally, we haven't decided, but you can probably guess. We can have a system that's anti-causal, which basically means the h of t is 0 whenever your t is positive. It's not really physical, but it's an interesting term to define. So yeah, if your system is anti-causal, which means let me just write it here. Maybe not here. Anti-causal, here it's okay. Yeah, anti-causal means h of t equal to 0 when t is bigger than 0. Okay. And yeah. There is not too much physical intuition here, except you can see this is the opposite of being causal. But anyway, so if you have this condition, then your system, your ROC should be left-sided, and you will get this impulse response, and you can see you can cut off this at this u of negative t. And that's why it's anti-causal. Okay, so yeah, so this is something we'll often do in this chapter. That is, you have a Laplace transform, and you can specify you want your system to be maybe causal and stable, and sometimes it's not possible, and or if it's possible, then you can pick the ROC, etc. Any question? So yeah, this is a very useful thing about Laplace transform. You can look at the ROC and know the stability and the causality of your system. Okay. And yeah, and just combining those two things, then then you can see that if you want to be stable and causal together, then you need to pick the ROC to the right side, and also include And the ROC to the rightmost also need to include the geometric axis. And that means all of your poles need to be left-sided, need to be left of your geometric axis. Okay, and that's necessary for usual system, and it's necessary and sufficient if you have a rational system. Right? So if you have a rational system and you want it to be causal and stable, then that's if only if all your poles on the left side. And then you can pick the ROC, that's the rightmost, and they will include the geometric axis. Okay. So yeah, that's really interesting. You have a rational system, you write down its, maybe you have a rational system from a differential equation, and you want to see is it possible that your system is causal and stable, then then you can really just look at the poles to see whether that's possible. If your poles are all left to your geometric axis, then that's possible. If not, then it's not possible. Okay. Oh, question? Yeah，胡同学。
老师不好意思，那个我还是有点搞不太懂，说那个就是同样是那个 example 的那个
前面
那个
这个吗
？9.17跟9.19，就是同样都是 s 大于-1，可是就是不懂说为什么一个是 causal， 一个是 non causal。
因为这个没有 rational 啊，它要if only if 的话，只有 rational 的嘛。这里有个 e2 的 s， 所以它不是 rational。rational 要每个东西都是 polynomial 嘛，这 e2 的 s 不是个 polynomial。
理解。
对。
了解。
Okay. Any other questions? Okay. If not, then let's see what more we can do. Okay. And yeah, then we get into a kind of differential equation. Yeah. Anyway, so let's look back to this second order system we talked about just last time. And we kind of solve the second order system. And okay, we missed a lot. We skip a lot, but so we have a second order equation, and we can solve for the system function like this, basically just reading from the differential equation. And we can get either impulse response like this. And so the order is more like we're starting from here. You can solve the system function, and it has second order. Excuse me. It has a power of 2 on the denominator, and there are 2 roots, and the upper part is basically just a constant. So there's no zeros. So you have 2 roots, it's C1 and C2, and if you want to do causal, and then you will inverse to this u of t, right? So, and yeah, so here we already kind of see we are getting this, right? So from our discussion, so you have 2 roots like C1 and C2, and want the system to be causal. So you want it to be causal here, right? You want it to be causal here, then you want to pick the ROC to the rightmost side, okay? And yeah, so that already determines what your impulse response will be, because you already picked the ROC, and that will make every factor correspond to this EAT U of t. Okay. So that's what happened. You have So you have this causal condition, you will determine your RC. And now we want to see whether it's causal. If it's causal, is it possible to be also stable? And then we need to read a little more into what actual value of those C1 and C2. And well, we already do the algebra here. So C1 and C2 look like those two things. And well, it's a little complicated, but if you think about it, you need to do this a little more careful. But you can prove that if C is bigger than 0, then this is always going to have positive real part, and C is less than 0, then it will have negative real part. Okay. Oh, sorry, I said the other way around. Okay, so if C is bigger than 0, then you have a negative real part. So omega is already real, and well, omega is real and positive. Okay, so yeah, omega is real and positive because it's like a frequency, and then we usually take frequency positive. And now it's XC, and if C is real, so if C is positive, then this negative C omega is going to be negative. There are other things, but it's not going to make it positive. Okay. So if C is bigger than 0, then the real part of C1 is going to be negative. And the other way, if C is less than 0, then this part is going to be positive, and actually the real part is always going to be positive. Okay. And C2 is actually the same thing. So this second term is actually always going to be less than the first term on the real part. And so that's a lot of time spending on saying this. But anyway, so what I want to say is, so whether C is negative or positive will decide whether the system, your second order system being causal system able to be stable or not. Because so the two roots will look like this. So this is when C is, so the absolute value is also less than 1. So you have the sign measuring part. And anyway, so if the real part is positive, and you want a causal system, so you pick the rightmost ROC, then you see this ROC doesn't contain the J omega axis, so this is unstable. And otherwise, if C is positive, then we'll have two roots here, and our C will include J omega axis, and the system will be stable. And it's also can see from here. So you have e to the C1, e to the C2 here, and if the real part is positive, then it's going to be exponential growing, and that kind of impulse response cannot be stable. And if you have a negative real part, then the exponential decay will be stable. And let's see if I can jump back really quick to second order. Where is it? Okay, second order equation is here. Right? So we had a stable system. So there are two cases. So where this term is imaginary, this term is real. But anyway, if C is positive, then we have the two roots always on the negative side. If it's real, then look like this, and if it's imaginary, it will look like this. But it's always on this side, so if you choose the causal system, then our C will be something like this. It will be right-sided, so it's causal, and it will include the J omega axis. So in this case, we have a causal and a stable system. And yeah, and you can, it's hard to see here. Yeah. Okay. Jump back, and Okay, yeah. So that's an example for second order system. And, okay, yeah, we can go a little more than last year. Or not? Yes. No, we haven't. Yeah. We are slower. Anyway, and then we can also solve differential equation kind of using the same idea. So once again, we have a differential equation. It's constant linear differential equation. And then we can try to solve it with Laplace transform. So right now it's very similar to Fourier transform. So the ddk becomes x to a k, ddk becomes x to a k. And you have a big Y equal to big H times big X. So you can write down big H with as this rational function to S. Okay? Some bk sk, some ik sk. And so that's one way to solve differential equation is you write down this system function by the Laplace transform we talked about, and you can apply some causality, stability to determine its RLC, then you can do the inverse Laplace transform. So that works, but that's without boundary condition. And in the last part of our course, which we cannot reach today, you will see that there is another weird form of Laplace transform, which is called Untitled Laplace transform. And with those, you can solve the differential equation with initial condition or boundary condition. But that is quite weird because you think about differential equation with boundary, with initial values, with like a fixed initial value, that's actually not the LTI system. But anyway, so that's hopefully you can reach next time. And today we'll see how to solve the differential equation like this. So it's kind of similar to what we do on chapter 4 where you do Fourier transform. So you see this is basically same as Fourier transform, you just replace j omega with S. But now you can pick different RLC. So in particular, in chapter 4, it basically only works for system that's stable, right? Now we can have solution of this for all kinds of weird systems. So basically is we are going to do, you write down this big of H, and then you will try to see which RLC you should pick from the stability or causality of the system. And so for example, C you can do is initial rest. So that's why we spent a lot of time talking about initial rest back in, I think, chapter 3. Yeah. So initial rest is equal to causal LTI. And now you can kind of see everything together. So if you have initial rest, then it's causal, and then you need to pick the RLC to the rightmost side. Okay. Yeah. So yeah. So you have a so we see that you have a differential equation and also the initial rest condition. Then that's enough to totally characterize your system. And because this initial rest will mean it's causal, and it means you can pick the RLC to be the rightmost part. And so an example here, differential equation. So first of all, the differential equation, dy dt plus 3y equals x of t. And then you can write down h of s really quickly. Move things around and skip that, and it's 1 over s plus 3. And so this has a pole at s equals to -3, and there are two possible RLC. So RLC is either the right side or the left side. And we've seen this many times. They have two different two different inverse Laplace transforms, so two different impulse response. And so, for example, if we think a system is causal, then we need to pick the right-sided RLC, and we know the impulse response will be this. Okay, and also you can say if it's stable and you want to include the geometric axis, then you also pick this. Okay. Question? Not? Then let's see a little more physical example. So this is RLC circuit, and let's skip all the physics. So if you do all the physics, then I guess we still want to say a little. So here you have RLC and capacitor, conductor, and the resistance. And so actually we want to say is X of t is driving voltage here. And Y of t is, I believe, the voltage on this capacitor here. So driving a system with some voltage here. You want to see what voltage you get out at this capacitor. And now if you actually do a physics, then you will look at this RC, LC here. And now this is linear constant coefficient differential equation. And you can write down H of S really easily. Just, yeah, it's going to be like this. Okay. And and yeah, so you look at this and you can solve for its poles. And so poles is like the roots of these things. And well, if you remember the formula for the roots of the second order equation is like 1/2 times minus b plus minus square root of something. Then the minus b is this minus r over l. And well, R, L, C are the physical parameter of those three components, and they should be positive real. So what we want to say is that the poles will have negative real part. And this is a physical system just driving like this, so it should be causal. So I pick the causal RLC, and all the poles has negative real part. So just like the picture we talk about like this. And so the system should be stable. Yeah. Because if the poles are all negative real, and yeah, it's stable. And it's also just an example of the second order system. Okay, it's like this, but the poles are actually negative real with the negative real part. Okay. And I think we are out of time. We're really slow. But anyway, yeah, any question about causality and stability by looking at the RC? If not, I think we are out of time, and we'll stop here today. Okay, and yeah, let's stop.